Hello everyone, this is a KDD 2020 tutorial, Recent Advances on Graph Analytics and its applications in healthcare. Thanks for your coming. This is Chen Xizang from Cornell Medicine, Cornell University. Please refer to this webpage for the tutorial materials and outlines. In this tutorial chapter, we will focus on graph generative models and drug discovery. This tutorial is based on our latest work on AI-driven drug discovery, MoFlow, and invertible flow model for generating molecular graphs. This is a joint work with Professor Fei Wang from Cornell Medicine, Cornell University. Drug discovery and development consists of following cascading steps based on the discovered target protein of a focused disease, then to screen millions of functional molecules to inform design. This step is called lead discovery. The next step is lead optimization, which means to design, make, and test more than 1,000 of new molecules with optimized property, and then followed by preclinical experiments and then human clinical trials, including 1, 2, 3 phases. Overall, going through such a path is very lengthy, costly, and always ending up with a failure. Specifically, the average cost of developing a successful drug is estimated to be $2.6 billion. And it takes at least 10 years to translate it into patients with only 12% success rate. Here, our works focus on lead discovery and lead optimization, namely drug discovery process in short, which takes approximately 5 years and accounts for 1/3 of the total cost. A critical question to be answered is how to accelerate the process to reduce its cost and to increase success rate. Even the first step, lead discovery, is very challenging. The chemical space is very big, but largely unexplored. The scale of drug-like small molecules is up to 10 to 60. However, existing chemical database is at the scale of 10 to 6. We can see such a huge gap between them. We cannot exhaustively enumerate all the 10 to 60 molecules. How to efficiently explore such a big chemical space is very difficult. Lead optimization, which tries to optimize molecules, is also very difficult. To design novel molecules with optimized properties needs to high throughput screen existing database or based on medicinal chemist knowledge. To evaluate the candidate molecules needs very expensive in vivo experiments or expensive in silico simulation. How to efficiently optimize molecules guided by the targeted properties is very challenging. Our vision is drug discovery driven by AI and big chemical data, with ultimate goal to reduce time, cost, and failure rate of drug discovery processes, maybe from 5 years to 5 months, to efficiently explore 10 to 60 scale drug-like chemical space, and to efficiently and automatically design novel molecules with optimized properties, leveraging both knowledges learned from big chemical data and the medicinal chemists. Specifically, we define our problem as follows. Our goal is to generate novel molecular graphs with optimized properties. Our data are discrete two-dimensional molecular graphs. For example, metformin on the right and its two-dimensional graph representation. We have multiple molecular graph samples and their corresponding properties. Our outputs are novel molecular graphs with optimized properties. Why is this problem very hard? First, we are faced with discrete molecular graphs, data, and their combinatorial complexity. Here, nodes represent atoms, and for example, carbon atom, hydrogen, oxygen atom, and so on and so forth, and edges are bonds. For example, single, double, and triple bonds in physics. Both nodes and edges have multiple types. The combinatorial complexity of the small molecule graphs space is near 10 to 60. Besides, existing deep models are majorly designed for regular grid structures instead of graphs with multiple edges and multiple types of nodes. Second, why is it very hard? Molecular graph optimization task is novel and very complex task, which consists of 3 subtasks, including graph generation, graph property prediction, and graph optimization. Graph generation means to learn a generative models, namely a distribution of graphs. Generation is just a sampling from the learned graph distribution, PG. Graph property prediction means to learn a mapping, FG, from discrete graph space to continuous property space. Graph optimization means to design new graphs, G prime, with optimized property. Thus, we need efficiently search discrete molecular graph space and sampling novel molecular graphs from this space. Guided, pay attention to guided by the property functions, which is a mapping between graph space and its property space. Third, why it's hard? Encoding graph is hard. Decoding graph is much harder. As discussed in the previous tutorial, we need to encode, or to embed, or to inference with graph inputs. To design molecules with a combinatorial structure is a reverse process, namely to decode or to generate graph outputs with multiple types of nodes and edges. What's more, the generated graphs are not trivial graphs. They must follow balancing constraints in nature to guarantee chemically valid molecular graph structures. And we also want to generate novel graphs as many as possible. Here we will introduce some related works on how to generate molecular graphs. One of the seminal work is Graph VAE model, based on the variational autoencoder framework. The authors try to generate small string representations of graphs. Here we can see the molecular graphs and its one-dimensional string representations. Their limitations are sequence loss a lot of structure information of molecules, and thus they show very limited performance. Junction tree VAE models tries to incorporate graph structures into VAE models. On the top right, we can see structure information of molecules is better kept by graphs. Two very similar molecules have quite different strings representations. And the junction tree VAE generates chemically valid molecules by capturing valence constraints on graph. However, GTVAE can only handle tree structure molecules, and the generation of molecules needs very expensive sampling in the latent space. GAN-based model, MoGAN, is also proposed for molecular graph generation. However, MoGAN cannot guarantee chemically validity of generated molecules, and GAN tend to have mode collapse problem. In this scenario, mode collapse means to generate a lot of duplicated molecules, which means they generate very few novel ones. The state-of-the-art results are achieved by autoregressive based models, for example, GCPN and Graph AF. They generate a molecular graph in a sequential manner. At each step, They generate an atom or a bond and then check the validity of the current graph. If the current graph violates the chemical constraints, the generation process terminates by reject sampling. However, the sequential generation is very expensive and they tend to generate very long and strange graphs as highlighted. RealNVP tries to generate molecular graphs by normalizing flow generative frameworks. However, they only use single add coupling layers in the normalizing flow structures. We will detail this part later. And its neural network structure is unstable to train, and their model can only generate very few chemically valid and novel molecular graphs. Thus, they show very limited performance. We summarize related works by their data. For example, sequence representations and graph representations, and their generative frameworks, including autoregressive model, variational autoencoder model, generative adversarial networks, and normalizing flow models, and their optimization method. For example, for VAE models and flow models, they tend to use gradient ascent method searching the latent space. However, for autoregressive models, they tend to use reinforcement learning to optimize molecular properties. Here, we focus on molecular graphs, normalizing flows, and naturally to optimize molecules by gradient ascent in the latent space. We will first introduce basics of normalizing flows and show why we choose normalizing flows as our basic generative frameworks. In this tutorial, we covered the basics of normalizing flow framework. Normalizing flow is an invertible generative model. We try to learn an invertible mapping f theta, which maps complex original space to latent space, which is a simpler space, say Gaussian. The generation process is a map from latent space to the original space by invertible mapping. We can learn the modeling parameters by exact maximum likelihood training. Each layer of the deep network structures must be an invertible layer, and the computational of the Jacobian determined. This part should be efficient. There are two constraints of such neural network structures. Here, we will first show one of the most basic structures, nice models. Nice models try to build invertible layers by splitting dimensions and use residual flow updated alternatively. For example, this is the input signals. They split into two parts, x1 and x2. They keep the x1 the same and use x1 after a transformation to update x2. And then here is the output of the latent space. They use x1 to save information for reversing and use x1 and this residual part to update x2. Thus, the reversing mapping is just as follows. How can we build deep models? So we can stack these layers layer by layer by alternating update different parts. For example, this layer, we keep x1 the same. For the next layer, we keep x2 the same, z2 the same. Another updates updates of the nice model is RealNVP models. They follow the same ideas, splitting dimensions and to build invertible layers. However, they introduce affine transformations. So instead of just the residual part, they multiply this by exponential scale to make it more powerful. And the reverse mapping is just as follows. Similar ideas to build deep invertible neural networks by alternatively update different parts. Later, the state-of-the-art performance in the CV community is achieved by GLOW model. GLOW models introduce another two layers to make it more powerful. The first one is ActNorm, which is a normalizing layer to make the learning dynamics more stable and which is also an invertible transformation. Another is an invertible 1 times 1 convolution, just like the graph convolution, but it's 1 times 1 convolution. So such a convolution layers makes the transformation more powerful and makes it can enhance the express powers. And also they follow the affine layers to build the invertible transformations like this. Why flow frameworks? We just summarize the state-of-the-art flow frameworks, but why we choose such an invertible mapping generative models? Because its invertible mappings enables generating more novel moleculars. For example, VAE, GAN, and autoregressive models are not invertible as shown in these diagrams. They can only reproduce, this is the training data, they can only reproduce part of the training data, and they can also generate some different extent of novel molecules. In contrast, flow models can reproduce all the training data by invertible mapping and generate more novel molecules, which means flow learns a strict superset of training data space and explores chemical space further and better. Besides, normalizing flow frameworks have following merits. They have exact maximum likelihood training. Compared with VAE and GAN, they are not. Efficient one-shot inference and generation, while autoregressive models generating molecules step by step, but our model can capture molecular graphs in a holistic way. Also, we will show the better performance later in the experimental chapter. So here is the idea of our MoFlow to generate molecular graphs. A molecular graph consists of atoms and bonds. Atoms are nodes with multiple types, for example, carbon, nitrogen, and oxygen, so on and so forth. So we can encode atom as a one-hot atom matrix. Bonds are edges with multiple types, for example, single, double, and triple edges. We encode bonds as a multi-channel tensor similar to image. In order to capture the discrete atom bond structures of molecular graphs, we decompose the probability of a molecular graph into two parts: the probability of bonds and the conditional probability of atoms given bonds. We can use any flow models to generate and to model to learn bonds probability PB, which generates the graph skeleton of molecular graphs. Given bonds, we propose a novel graph conditional flow FA given B to generate atoms given bond skeleton. Then we assemble bond atoms and bonds into a chemically valid molecular graph. We illustrate our model as follows. We use a GLOW-based model to model bonds probability PB, which encodes multi-channel edge tensor into latent space. Given bonds, we propose a novel graph conditional flow FA given B to encode atom matrix given bond tensors. We encode the discrete molecular graphs into continuous latent space, modeled by simple Gaussian distribution. We can sample from latent space and use inverse mapping to generate bonds tensors and atom matrix, respectively. And then we assemble atoms and bonds into a chemically valid molecular graph. Here are some details. We use a variant of GLOW for bond generation. Here we transform edge tensors by a variant of GLOW framework. First, we squeeze edge tensors to make it have more channels, just like this. And then use the same act norm layers to make the signal normalized and make sure the deep structures are stable. We also use invertible 1x1 convolution to transform the edge signals, and use the split and affine transformations to build and update the edge signals and keep them invertible. Here, we use sigmoid instead of exponential to make the affine transformation more stable. And we use 3x3 convolution, batch norm, and ReLU to transform B1 and to update B2. We can use arbitrary neural network structures here. We can build deep structures by alternating updating. Here is just a one layer of invertible layer. As we discussed, we can use any flow to learn bound tensors probability PB, which generates the graph skeleton. However, to generate atoms is not trivial. Given bonds, we propose a novel graph conditional flow for atoms given bonds, skeleton. Here we use both atom matrix and bond tensor as inputs. First, we also use active norm two-dimensional to normalize atom matrix and then follow split techniques to build invertible structure. For each layer, we only update each atom and each row by the remaining atoms and their link structures. We use the remaining atoms and their linked structures by a multi-channel graph convolution. We convolute each channel of the tensors and then sum their signals. Here we use multi-channel graph convolution, batch norm, ReLU layers, and a multi-layer perception to summarize their information. Here we also use affine coupling structures to make it an invertible transformation. Also we use sigmoid here. We can build a deep invertible neural network by alternating update in the next layer. All right, here are after some math details. Again, let me show the overall structures, frameworks of our model. Our MoFlow can embed or inference or encode discrete graph structures into continuous latent space. And the generation is just sampling from this latent space and use its reverse transformation to generate the molecular graphs. We can also use another multi-layer perception, which mapping from latent space to property space to do molecular graph property prediction tasks. So here is for regression. Thus, guided by the gradients of the properties, these regression parts, property prediction parts, we can search the continuous latent space of a molecular graph and then generate optimized molecular graphs. We check the valence constraints by this equation. The number of bonds linked to one atom, I, should be smaller or equal to the valence of these atoms plus its formal charge. For example, a carbon atom can have 4 bonds. An oxygen atom usually have 2 bonds and up to 3 bonds when it has extra charge. We modify the generated molecular graphs into a valid one by this validity correction process. If the current molecular graph follows valence constraint, we return its graded connect component. Else, we delete unnecessary bond or add additional charge to the invalid atoms according to chemical rules. We validate our models by 4 tasks, namely molecular graph generation and reconstruction, visualization of continuous latent space of graphs, molecular graph property optimization, and constraint property optimization. We'll elaborate each one in detail. The first experiment is molecular graph generation and reconstruction. The problem is as follows. Inputs are molecular graphs. Our models try to learn a generative models, i.e. the probability distribution of graphs and its invertible mapping F. Generation is just sampling from the latent space and use the invertible mapping to generate discrete graphs. Reconstruction is try to reconstruct the molecular graph from its latent representations. Our goal is to generate valid, unique, and novel molecular graphs. Here we use two famous molecular graph database. One is QM9, it's a relatively small database with at most 9 nodes. And the Zinc is a much larger one with at most 38 nodes. How to evaluate our generation performance? We use following performance evaluation metrics. Validity, which means how many chemically valid molecules are generated by our models. Validity without correction or check, because some models use post-hoc corrections, and our models use corrections to ensemble them. If our method don't use them, what are the validity performance? Uniqueness measures the percentage of the chemically valid and unique molecules in all the generated molecules. Because some models always generate duplicated molecules. Novelty is a very important one, which means to generate a novel molecule which are not exist in the training database. Reconstruction rate means how many data set we can remember and reconstruct from their latent representations. Here, we can summarize above ones by NUV, which means the percentage of novel, both novel, unique, and valid molecules in all the generated molecules. Here is a matrix. We propose a comprehensive matrix to evaluate the model, different models. Here our models compare all the state-of-the-art methods. For example, all the flow-based models, graph MAP, graph GRF, and graph AF. Our models guarantees 100% validity. If without corrections, our models also achieve the best validity. Our models can generate very diverse and unique molecules and also achieves the top novelties. Thus, our model achieves, we can generate more novel, unique, and valid molecules. Because our models are invertible, which guarantees 100% reconstructions. Here we also compare the VAE models, autoregressive models, and flow models. Our models can achieve 100% reconstructions. Best can generate more novel, unique, and valid molecules, and 100% valid molecules. And if without correction, our model also achieves the best performance in validity compared to the state-of-the-art results. Thus, our MoFlow explores the big chemical space further and better. Here we visualize the latent space of our model. Our model can encode and decode between discrete graph space and continuous latent space. For example, here we create interpolation around the latent representations of one molecular graphs and decode its neighbors. Here we visualize the decoded molecular graphs. We can see the latent space is very smooth by checking their graphs. Their graphs are just change a little bit. We measure the graphs, the similarity between different graphs to the center graph by the Tanimoto similarity. We can see the graphs change gradually in this two-dimensional latent space. We further do a very famous experiment, just as in the CV, a linear interpolation of phases. Here we do a linear interpolation between two molecular graphs. Here is the one molecular graph, here is another. We can see if we sampling from their latent space, the linear latent space, we can see a very smooth changing trajectories from one graph to another graph. We can see their similarities become their dissimilarities become larger and larger. The third experiment is property optimization, which means to generate novel molecules with the best quantitative estimate of drug likeness scores, QED scores, as many as possible. We search the latent space by gradient ascent and try to generate the best and report the best molecular with the top QED scores. We can see the best performance by the VAE scores, autoregressive plus reinforcement learning methods. They can only generate two molecular with the best 0.948 molecular graphs. However, we can see our MoFlow generates more novel molecules with the top QED scores. Here are top QED scores. We rank the top generated novel molecules. Our models can generate much more than the state-of-the-art results. Here we just show some the performance, visualize some molecular graphs. All these molecular graphs are with the best QED scores. The first experiment is constrained property optimization, which means to find a new molecular graph G prime from a seed molecular graph G. To maximize the similarity and the property is kind of multi-object optimization. Here we use Tanimoto similarity of Morgan fingerprint to measure the molecular graph similarities. For target properties, we use a comprehensive one named penalized log P, which is the octanol water partition coefficient log P, penalized by the synthetic accessibility SA score and the number of long circles. Here are the results. We compare our models with the state-of-the-art methods, GTVAE, GCPN, and GraphAF. Our model achieves the best similarity and the second best improvement. However, compared with the best improvement, our models can generate more realistic ones because the best performance are achieved by this particular long chains. However, we can see our models can optimize molecules by in a very subtle way. We can see this part. So this molecular show very worse scores, but our optimization methods just change it a little bit, and we keep the best similarities and improve these moleculars to a very large extent. Here we also randomly sample some molecular from the zinc datasets and optimize them. Here we can see our methods optimize the P log P by a very large margin from this large circle to these ones, and these ones to these circle ones to these ones with much better properties scores. So in summary, we propose a novel MoFlow model for molecular graph generation, which consists of a variant of GLOW for bonds, a novel graph conditional for atoms given bonds, and which has a novel validity corrections to ensemble them. Our model is an invertible model with a fast inference and generation at one shot. Our model also achieves the state-of-the-art results. That's the results for generation and reconstruction with respect to novelty, uniqueness, validity, and reconstruction rate. That's the results for QED property optimization. We can generate more drug-like moleculars. Fast similarity scores for constraint optimization and the second best improvement scores for P log P. Please kindly refer to our paper MoFlow and invertible flow models for generating molecular graphs for more details. And more information can be also found in my web page. Thank you so much. So let's give time to the next section, discussion part, and I'm very happy to take any questions later. Thank you so much.